Well, thanks everybody. I appreciate your time coming into the talk. As you mentioned, I'm Ralph Poor. I'm with Surface Combustion, now going on 33 years, and primarily I've been involved over the years with the standard products, the process controls, the ion nitriders, the vacuum furnaces, the endo generators, and the all-case integral quench type furnace. So I've been around for a while. I was involved heavily with vacuum from around 1990 to about 1995, and involved with vacuum carburizing from about 2000 to current, but a lot of work on research back around the year 2000 to 2004. Could I have a show of hands of people that have vacuum equipment now or have vacuum tempering? Okay, so we've got maybe half of the audience has experience with vacuum, so that's good. I'm going to talk specifically about vacuum tempering, and in a nutshell, you know, for the people that are saying, where does this fall, you have tempering pretty much of all metals after heat treatment or after hardening. Some people will do this in air, and that's going to be the greatest source of oxidation. Then you would move up to perhaps a direct-fired furnace where products of combustion should actually oxidize less than just being in air. And the next motion up, or the next piece of equipment up after that, would be a nitrogen temper. And now in the nitrogen temper, you're displacing the air or the products of combustion, but you typically open this furnace up to the air, and at some point in time you need volume changes, ideally 5 or more, to get most of the air out of the furnace. Vacuum tempering equipment I would consider the high end now of the spectrum, where we remove all the air and then we backfill with one charge of nitrogen. So that's kind of the continuum on getting better, and better yet. The price of the equipment goes up also, kind of at about the same rate. But we've seen where people will struggle with nitrogen tempers, where they're just going to flood the furnace for a long time. They'll get the air out, or a good share of the air out. But now you have to either cool the parts before you pull them out in a nitrogen temper, or what I never really could figure out was just pull them out into the air, because now you've really, at this point in time, have oxidized them. Some people go, yeah, but they're not really sitting in the air for hours and hours and hours, and I would agree, yeah, that's better yet. So we'll look at vacuum temper equipment. This is a traditional vacuum temper that we would build. This would be a 3648. 36, standard size for us. We build smaller, we build larger. So why would you go to the expense of a vacuum temper over just the air and the nitrogen? Number one, part finish. So if you have parts that have already been processed in a high temperature vacuum furnace, this material comes out very shiny. Why turn around and put them into an atmosphere temper and discolor them at that point in time? Vacuum tempering equipment, we traditionally see plus or minus 5 for uniformity. Plus or minus 10 is very easy to do. 5 is easy to do, and we have equipment that's even on the order of plus or minus 3 and 4. Nitrogen usage is low in that we remove all the air from the furnace, and now we just backfill it with one charge. So instead of running 300 cubic feet per hour for 4 or 5 hours, we're going to run just 300 or 350 cubic feet one time in a 3648. So nitrogen usage is low. We actually had one customer was able to justify buying the vacuum with a 1-year payback on what he would have spent on nitrogen. This was a much larger furnace. We've got some photos of that application. Another ideal thing you'll see about a vacuum temper is they're environmentally friendly. You don't need a pit. You can put them right on a manufacturing floor. All you're going to do is drop 480 to it to run the heating system, to run the fan. You're going to drop a nitrogen line, and you'll probably have a PVC takeaway pipe for the vacuum pump, and that allows integration into manufacturing for a captive type environment to go quite well. And as I mentioned, traditionally no pits required for any of the horizontal units. We build vacuum tempers without a water-cooled casing. And so what we basically have is just a single wall steel shell, dished heads on each end. But when you take water out of the equation with a high temperature process, these units get extremely safe. When you get into conventional vacuum processing, you got to make sure that you have excellent inner wall integrity, because high temperature and a water leak is a bad situation. So in this case, the water systems are pretty much only used for cooling. Vacuum tempers also only run the vacuum pump to evacuate the furnace prior to the backfill. So the vacuum pump might run 15 minutes and shut off for the rest of the cycle, which could be 2, 3, 4 hours easily. So the vacuum pumps get a lot of long life. And then you don't have your traditional pilots and flame screens and effluents burning that you would have on traditional atmosphere furnaces. This particular furnace is a larger 60 by 96 by 60. It's doing wire mesh and wire screen product, and you can kind of look into the back and you'll see a operator with a loader give you a feel for how big the furnace is. This particular model is a gas-fired unit. We build both electric and we also build gas firing. So for those of you that have low natural gas rates, which is now pretty much everywhere in the country, gas firing makes a lot of sense for those people there. This particular customer was the one that actually had a very short payback strictly on the vast amount of nitrogen that they were going to be using. This wire mesh has really slow heating rates and slow cooling rates. And so they had a 24-hour cycle that they would have been running nitrogen the entire time and some pretty high flow rates. So in this particular case, they would do one charge. And you can also carry the one charge into double temper and triple temper for tool steels. And that is additional savings. The system's set up where you can either, after one heating and cooling, re-evacuate that nitrogen and go back with a clean charge to do the second temper, or you can program the system to just do one charge, heat it, cool it, heat it again, cool it, heat it again for as many temper cycles which you might need for a tool steel. Could be 2, could be 3, could be 4. Example of the type of product this particular customer runs. They've got moldable furnaces, and they're doing copper plated, they're doing steel. Some of their product is going to get E-coated, and so they need clean product for the coating processes. They need clean product for what they sell in just bright finish. A little bit about how they operate. They start cold. So when you approach the furnace, it's already down to room temperature from the last heat treat cycle. You're going to load the furnace, and then the vacuum pump turns on along with the evac valve opening. You'll pump down to traditionally 25 microns. You can go lower, you could go as low as 5 or 10. Some people say 50 or 100 microns is good enough. So that's up to you. It's just a setting on the control system. Once the system has pumped the furnace down to this level, 20 minutes depending on the size or the vacuum level you're going to, we backfill to atmospheric pressure with cryogenic nitrogen, one charge. 3648 furnace would use roughly 320 cubic feet. Then the heating system turns on, and we're actually heating under convection. Most people will run at 1 bar convection. We have equipment that can run at 1 or 2, so you get a faster heating rate. At 2 bar, you get a faster cooling rate at 2 bar. And then during the cooling cycle, after the soak is complete, there's a contraction that happens as the gas cools. So as that gas cools, we'll add additional nitrogen for a few seconds, and that'll bring the pressure back up to typically 1 or 2 bar. At the end of the cycle, we'll vent off any excess pressure we might have. Then we'll open the door, the parts are cool, and the load is removed, and you can reload the furnace for your next cycle. This is an illustration of how we build most of our vacuum tempers with a rear-mounted fan. We have a fan in the back that brings the wind out in a circular fashion around the heating elements and sends that wind toward the front of the furnace where it's drawn back into the center of the load. So there's actually two wind swirls or wind patterns. There's an outer pattern that's sweeping the outer part of the load and sweeping the heating system, or it could be sweeping the cooling system doing cooling. And then there's a section that goes into the center of the load, or back into the center and back into the fan. We get this question a lot, and this is actually a viable way of vacuum tempering, is that if you have a high temperature vacuum furnace, just temper in there. But what you'll find is that a lot of the tempering of tool steels is done at 1,000 degrees, and you'll find that a traditional hard vacuum furnace at 1,000 degrees takes a long time to heat a load. We've actually seen it take as much as 12 hours on a dense 3648, 36 load with multiple layers and multiple rows. You'll find that the uniformity is not so good at 1,000 degrees, and you'll also find that the temperature control in hard vacuum at 1,000 degrees tends to oscillate quite a bit, and you have to have, of course, special PIDs to help at that. When you get into convection heating in a vacuum temper, you'll find that the uniformity is excellent. You'll find that the heat up rate is as good as it gets, and you'll also find that the control can be held within just a couple degrees, which also is another benefit. So those are the big things about why you wouldn't do it in a conventional high temperature vacuum, even though many people do and it can be done. What are some of the other applications? I mentioned the tool steels. That was really my first experience into this particular piece of equipment. We had a lot of commercial heat treaters buying them, so they were doing H13 tempering, A2, D2, etc. Wire cloth, as we talked about, and the wire cloth, again, in this particular example is just low carbon steel, but it's got really long cycle times. Copper fittings and copper sheet. So if you have any particular applications where people are making copper valve bodies, tubing, fittings and whatnot, copper is a beautiful one that'll come out bright. It's extremely forgiving, extremely easy to do. We've got applications for beryllium copper. So there's people doing electrical contacts, springs and clips. It's typically done in the second process at about 600 degrees, so it's a nice application for the furnace. You can do all your alloy steels. You can do stainless steels, but we typically recommend a 4% hydrogen addition with the nitrogen. It'll keep stainless bright. You'll get some discoloration. And again, discoloration's in the eye of the beholder. One guy can look at that and say, that's the most beautiful part I've ever seen, and somebody else look at it and throw up. So we typically, when you get into the stainlesses, will recommend a 4% hydrogen addition. People use it for medical equipment, small parts, computer parts, and also a number of our customers use it for heat flattening. So they want to have a pristine atmosphere. They don't want to get sticking of the parts. They want to have bright parts, and the vacuum tempering works good on that particular process. How are they put together? Traditionally, it has a round casing that's rolled. We roll it from 3/8 inch steel. The back of the furnace has traditionally got a welded dished head. Again, this is single wall, so there's not a water jacket in it. When you get into water-cooled casings, water system maintenance is the best thing you can do in keeping that water always flowing. The worst thing you can do is shut off a water system to a vacuum furnace and just let the water sit in there and stagnate. Treat the water, keep the pH levels up, flush it, have rust inhibitors added to your water, and you can get 30 years, even 40 years of vacuum furnace life. We build them without a water jacket, so all of those corrosion issues just go away, and that ends up making this furnace one that will last for decades and need very little attention. We typically sell them with an autoclave locking ring, So you'll find that there's a ring that rotates with a hydraulic power pack, and it allows the door to be clamped down. And we want to have pressure on the door if we backfill to 2 bar or if we backfill slightly positive, so we don't have any type of air infiltration at that point in time. Traditionally, during pumping, the doors pull in and an autoclave's not really needed. But it's a nice optional feature that pretty much everybody buys. Inside, we build a ceramic lined using a 8-inch module, and these have a stainless steel rod that is welded to the casing. I don't want to say it's a lifetime insulation package, because all of a sudden at some point in time it wears out and somebody's going to come and say, you said lifetime. But the systems that we have sold dating back to 1990 all have their original insulation package in them. So those are welded blocks, and then we put a rigidizer on them, which keeps wind during heating and cooling from eroding the surface of that. Keeps any fibers from wanting to radiate out. This particular model, you'll see a heating element, and the heating elements are mounted at 3 o'clock, 6 o'clock, 9, and 12. This model also has what we called intercool, which was a cooling tube that had water introduced only during the cooling cycle. We have some performance data to show you on that. There's a stationary hearth that is, find my LED here. It's a little washed out. I think the batteries are dying. Stationary hearth, and that ends up providing very little interference to wind, and then the fan is mounted on the rear wall. We build it in 2 different hearth configurations. For people that want to go up to a 4,000-pound load, we put in a little heavier version. And what you'll see also is that they're traditionally loaded with either a fork truck or a Big Joe type loader. We do have designs where you could actually load it with an all-case style or integral quench style charge car. We changed the door for that particular setup. There we go. Here this shows a actual gas-fired radiant tube. So we've got this actually mounted, one under the load at 6 o'clock, 9 o'clock, 3, and 12. Cooling systems. We've built a lot of these with what we call internal or intercooled cooling. We had 8 horizontal tubes which had a finning over the OD of the tube. And then in the center of the tube, which was actually a 330 type material, we had a stainless steel helix, and we would put water through that helix at the beginning of the cooling cycle. So we would run 8 of these traditionally, and it allowed the furnace to be smaller and simpler, and we've built a lot of them with this particular design. Water usage is low. This design runs about 3 GPM per tube, and it's a very simple system.
What temperature is that water?
Room temperature.
Yeah.
So the water, there's some steaming that happens as the water first turns on, and so the tube basically has no water in it from the last cycle, and then during the cooling stage, which could be, at 1,000 degrees or 1,200, we then open a solenoid valve and the water starts to flow through this helix. And it flows through the helix. This is all within the cooling tube itself, and then at the end it returns back and floods the helix and floods the ID of that cooling tube. Yeah, normally people, you would have some type of water system that would then have either a evaporative cooler up on the roof or outdoors, or you'd have a heat exchanger with a cooling fan. Yeah, it would be expensive to use tap water or city water for this because of the waste, but most people just have a system for that purpose. We also build an external cooler, and the external cooling system, as you can see here, is sitting up on top, and we have a blower and heat exchanger all within that system. So when it's time to cool, we actually activate the cooling blower, and the cooling blower then circulates air or the nitrogen, not air, but circulates the nitrogen through the heat exchanger. You can see a couple of the hoses coming down for the heat exchanger is located inside there. And the other thing we can do with the external cooler that we really can't do with the intracool design is if you want a slow cooling rate or a controlled cooling rate, we can actually put a VFD on this blower and actually cool at a rate. As where the R system is more like a high pressure quench furnace where you start cooling and you're not going to stop. You're just going to keep on going. So this particular unit has more flexibility with that. Both are compatible with of course, the nitrogen or the hydrogen-nitrogen atmospheres. And as I mentioned, the heat exchanger and the blower are mounted in one cooling enclosure. We originally built them with separate, so there was a blower that we bought with vacuum service, and we had a separate heat exchanger can. And there's more potential places for leaks, and it's more expensive to build it as two pieces of steel. There's more flanges. So this simplified construction and reduced leak points. This kind of just gives you a feel. This was a 1,500-pound load, and intercool would bring that down from 1,000 degrees roughly to, and I always kind of call it at about 150. If you're doing stainlesses, you'll want to get them down to 150. If you're doing carbon steels, you could actually pull out sooner, and you can pull out sooner with copper too. But for your stainlesses, they're more prone to discoloration, so you'll want to get the loads down as cool as possible. So this shows approximately getting to 150, taking somewhere about 2 hours. The external cooling system would get you down to 150 in roughly 30 or 40 minutes. This is a closer example. This has also got some load couples and shows you the comparison between wind temperature and load temperature. So again, this was a 1,500-pound gross load. We soaked it at 1,000 degrees. In this particular application, the customer said once the load couple or the buried thermocouple reached 1,000 that the soak was complete. We then start the cooling, and the yellow line is basically showing wind temperature or furnace temperature, and this is taking roughly 30 minutes to get down here. The load, on the other hand, is taking a little bit longer naturally, and we're calling it, well, actually it looks like here's about 120 degrees. So up in this area here would be your 150 roughly. So you're looking at approximately an hour to bring a 1,500-pound load down to 150. So that'll give you a feel for cycle times and cooling rates.